Hello everyone, nice to see you. So today we continue our work with trap-assisted recombination. Last time we stopped at this slide. Actually, we derived the equation for net recombination rate of Shockley-Ritz-Hall recombination or trap-assisted recombination via deep energy level located in the band gap. And we see here capture cross-sections, capture coefficients for electrons and holes, which are given as the product of capture cross-section and thermal velocity of electrons and holes, respectively. Here we have product of total concentration. So it actually equilibrium plus non-equilibrium charge carriers. Intrinsic charge carrier concentration in second power. Also in the denominator, what is important, we have these guys N1 and P1, which stand for their physical meaning is equilibrium charge carrier concentration. When someone can tell me how do we define this P1 equilibrium charge carrier concentration? Let's say N1, equilibrium electron concentration in the conduction band under which condition? Energy, yes, something about energy.
Yes.
Of this energy level. Yeah. So when Fermi energy coincides with the energy of the trap, which this trap-assisted recombination is going on. So the same stands for P1. So it means that these two parameters, they depend on the position of the energy position of the level associated with this defect or impurity in the semiconductor. So after several modifications, when we consider that N is actually the sum of equilibrium and non-equilibrium charge carriers, delta N and delta P, assume that delta N is equal to delta P. Sorry. Then we can also express Ni as a product of equilibrium charge carrier concentrations in the conduction band and valence band. And eventually, when we take it out of parentheses, we get this final expression for net recombination rate. So that's the moment when we actually stop our discussion last time. And today, hello, sit down please. And today we need to introduce recombination lifetime under trap-assisted recombination conditions. So from previous discussions, when we considered bimolecular recombination, we know this general definition of recombination lifetime, which is the ratio between excessive non-equilibrium charge carriers to the net recombination rate, which actually tells us how much time it will take to let all non-equilibrium charge carriers to recombine and be vanished. So taking this into account, substituting here instead of net recombination rate our equation which we derived on previous slide for trap-assisted net recombination rate, we get the following equation here. After splitting it into parts, we get two terms responsible for recombination lifetime in a semiconductor when we deal with trap-assisted recombination according to Shockley-Ritz-Hall statistic. So we have several parameters which play the role, capture cross-section for holes, concentration of recombination centers per unit volume, also position of this energy level because it defines N1 and P1, and equilibrium as well as non-equilibrium charge carrier concentration. So all parameters are here, and this is a good point when we can consider a different excitation conditions, similar as we did for bimolecular recombination. So now we have this expression for recombination lifetime, and first is low level of excitation when we assume that excessive non-equilibrium charge carrier concentration is smaller than both equilibrium charge carriers, and this concentration of charge carriers, equilibrium concentration of charge carriers, assuming that Fermi level is coinciding with the position of our recombination center. Opposite to this, we have high level, or it's actually level of excitation, and as opposite, we have much higher concentration of photo-generated charge carriers than any other charge carrier concentrations which we deal with during this discussion. So first, low level of excitation we can neglect with these terms because they are much smaller than others, and we have some here in the numerator and denominator. That's why we go from first equation, like general equation, to this a bit more simplified, associated to recombination under trap-assisted recombination under low level of excitation. So what's interesting here, we see that the most important recombination lifetime is not anymore a function of concentration of non-equilibrium charge carriers. So at low level of excitation, we need to care only about properties of the semiconductor itself, which are determined by equilibrium charge carriers under thermal equilibrium conditions, means on doping concentration, on either it's N or P type, because N0 and P0 will be different. Also on the band gap, because it will also determine concentration of equilibrium charge carriers. However, also we have this N1 and P1. And from here, looking at this expression for tau, we can already make some important conclusion. So let us consider at which condition this tau recombination lifetime will reach the minimum value. So from your point of view, what does it mean that we reach the minimum value for recombination lifetime? It means that we have the most high or the slowest recombination rate? High, yeah, because it's reversely proportional. So the higher recombination rate, the faster we will get rid of our equilibrium charge carrier concentration, non-equilibrium charge carrier concentration. So means we want to consider at which condition this recombination via trap will be the most important and the fastest. So in this case, take a look on this expression. So let us consider specifically parameters N1 and P1, because we want to determine it for position, this condition of minimum recombination lifetime, for position of recombination energy level. So we have in both terms of this equation, N1 and P1, they are in denominator. So we will get minimum recombination lifetime if N1 and P1 will have minimum minimum values. What is the minimum value for equilibrium charge carrier concentration in a semiconductor? Any ideas?
What again?
What is the minimum equilibrium charge carrier concentration in a semiconductor? You are genius, but of course we have a bit different, larger than zero number. So of course technically zero, but if we are talking about not zero Kelvin temperature, like room temperature, then it will be high, and it will be determined by the band gap, means it will be equal to intrinsic charge carrier concentration. There is no option to get lower charge carrier concentration because we have band gap and there is some thermal activation from valence band to conduction band that will result in some intrinsic charge carrier concentration. So minimum value for NT and PT, this will be Ni. And when we get intrinsic charge carrier concentration in semiconductor, in terms of position of Fermi energy. For intrinsic semiconductor, which is not doped, where Fermi energy should be located? Fermi level. In the middle of the band gap. Means we will get minimum values for NT, PT, which is equal to Ni, only by definition of this NT and PT. We repeated this definition when Fermi level coincides with the energy recombination energy level. And that means that this recombination energy level should be at the middle of the band gap. So it should be located in the middle, somewhere close to the middle, but ideally like right in the middle. It actually depends on the ratio between effective masses, but that we will not go into so much of details, but in the vicinity of the middle of the band gap. So then we will get conditions when this tau will be minimum. So that is clear. Now, if tau is minimum and recombination rate is maximum, and that happens only when position of this energy recombination level is placed in the middle of the band gap, means that the most efficient recombination center will be located in the vicinity of the band gap. Means it will be a deep energy level, which is located as far as possible from both bottom of the conduction band and top of the valence band. So means here in the middle, if we place some defect or doping atom inside the semiconductor, which creates energy level placed in the middle of the band gap, this energy level will work as the most efficient recombination center and will make the biggest contribution to total net recombination rate via this trap assisted mechanism. Okay, so this is important, keep this in mind, don't forget about this. So now we go to high level of excitation. So now delta N, excessive concentration, is much higher than all other concentrations and not P naught and NT-PT. So here we can actually neglect with these guys because in comparison to excessive charge carrier concentration, they are much smaller. So that's why, based on this result, we will see that recombination lifetime will be determined by this simple equation, which takes into account only features of the defects, because we have this capture coefficients for holes and electrons, and in the denominator concentration of our recombination centers, means concentration density of defects per cubic centimeter. So the higher this concentration of traps, defects, or impurity atoms which form these recombination centers, energy levels in the band gap, the smaller will be recombination lifetime. So from here we will also see that it actually as opposite to bimolecular recombination. If you recall our first lecture, I have shown that in the case of high level of excitation for bimolecular recombination, recombination lifetime does not stay as a constant value. It is a function of excessive non-equilibrium charge carrier concentration. It means that we deal with always with some instantaneous value of recombination lifetime, which changes over time as non-equilibrium charge carriers recombine over time and reduce their concentration. In the case of trap-assisted recombination, both non-equilibrium condition, both low level of excitation and high level of excitation provide us with a constant value of trap-assisted recombination lifetime. However, in the case of low level of excitation, as we discussed on the previous slide, we have this value determined only by properties of the semiconductor and position of the energy recombination energy level. And in the high level of excitation, we get tau recombination lifetime, which is determined by the properties of the defect, CN, CP, capture coefficients, and their concentration. But in both cases, it's just a single number, which is determined by a set of parameters and does not change over time as recombination happens and concentration of non-equilibrium charge carriers reduces. So with this, I would like to go to second part of trap-assisted recombination, where we will consider some disordered case. So what is important to know? Most semiconductors which we discuss here, they are based on crystalline structure with some periodic structure of atoms, and they are placed in the right position, and that means we have very sharp edges of the conduction and valence band because it corresponds to this periodic crystalline lattice. E, C, E, V. However, if we have so-called amorphous, where the conditions were not favorable for the formation of very periodic structure and atoms are kind of placed all over the place, and we don't have this long-range periodicity of the crystalline lattice, or for instance organic semiconductors, which by definition, since they are obtained from spin coating and from some polymers, cannot obtain this long-range periodicity. Then we have intrinsic feature as disorder in crystalline, in the structure, and energetic disorder, which results in some Gaussian or exponential distribution of density of states. And instead of having this sharp EC and EV, we have some tails. So maximum of this density of distribution, there is some function, let's say J as a function of energy, gives us concentration of charge states per cubic centimeter per electron volt, because they are distributed in energy. And that means that these tails, they consist of some localized energy levels, which are kind of going into the band gap of the material. So they're not supposed to be there, but they are there because this not structured, not organized structure of the material. So amorphous and inorganic and organic semiconductors, they possess a picture like this. So we have some tails of density of states which kind of go into the band gap. So we need to do something with this. So this is how we can consider ideal crystalline structure with conduction band and which consists of delocalized states. So electrons, if we have some electron here, it can easily move, and some disordered semiconductor, amorphous or organic, when actually these tails consist of some localized states placed close to each other, and electrons, they cannot just move easily in this because these states are localized. So there is some hopping mechanism. They can kind of jump from one localized energy level which is located close to them to another. In order to happen this hopping mechanism, we need thermal activation. So if these energy levels are located close to each other, we don't need much of thermal activation in order to happen to realize this hopping mechanism. So this is the way how charge transport happens in disordered semiconductors. But here we want to focus specifically on recombination. So if we have some deep energy level, we know what will be the net recombination rate of trap-assisted recombination. It is possible that we also have some localized single energy level in the band gap of amorphous semiconductor, but besides that, we also have these tails of localized states, and they also can participate in recombination process because these are localized states. They can trap charge carriers like electron, and then from valence band, and then from the conduction band, and then trap electron hole from the valence band, and participate in trap-assisted recombination. So we need to understand how it is possible to take into account the presence of these tails of localized states in the band gap in order to calculate trap-assisted recombination. So in this case, how it works? We consider, first of all, contribution from this single energy level in the somewhere deep in the middle of the band gap. So this stands for this R naught, which is the net recombination rate via single energy, deep energy level, which we discussed during previous and these lectures. However, then we need to add two contributions originating from the tail of localized states next to the conduction band and tail of the density of states next to valence band. So that's why we integrate from minus infinity to EC, so we kind of go from here up to here. And in that case, we will take into account contribution of trap-assisted recombination via all localized states which are in this tail next to conduction band. So you can see we have actually the same equation here as we derived previously in this integral. It's just here it stands instead of N1, and this stands instead of P1. So it's N1 and this is P1. And instead of NR, which we used as a fixed number of some recombination center concentration, we use here actually density of states for these tails which extend in the forbidden energies defined by the band gap. So when we have this distribution, it's either Gaussian or exponential function which describes distribution of these tails. We can, for each energy, we'll have certain amount of, means for each energy, like here, 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 we will have different numbers of localized states, and by multiplying them to the equation which describes net recombination rate for trap-assisted recombination based on shock-leaded Hall recombination, and integrate it all over the energy distribution of this tail, will give us the contribution of this total contribution of these localized tail states towards the trap-assisted recombination. Similar we should do for energy states next to the top of the valence band. In this case, we go from infinity to EV, means we integrate in this direction, and cover all contribution for trap-assisted recombination in by localized states in the tail next to valence band. So that will give us three contributions, one from the deep single energy level in the band gap, and also tails at the valence band, the conduction band, and valence band. That all will, in sum, give us the total net recombination rate. Yes?
But we consider this band gap region twice?
Consider this band.
This integral range from minus infinity to the conduction band.
Uh-huh.
So this is the first.
Mm-hmm.
And from the infinity to the valence.
We actually do not get twice because we consider, let's say we have J1 X for this tail, and then we have J2, X, energy, E. And let's say some other function for tail distribution here. Then when we integrate first time from, let's say, minus infinity to EC, for first function J1, we don't have any tails here. Tail stays here. Then the product will be, so this J1, G1 E will be equal to 0. So we don't have any contribution to the integral. We will get contribution to the integral only in this region where, this function is.
Because we have two G.
Yeah.
For conduction one.
Yeah, one for conduction, one for valence band. So we separately consider them, and that helps us to integrate, to get the total contribution. Okay, so this is the feature how it is possible to take into account so-called continuum of localized states in the band gap of the semiconductor. Now, as you remember, I specifically highlighted your attention, focus your attention on this fact that the most efficient recombination center will be that one which has energy level close to the middle of the conduction, to the band, in the middle of the band gap. So means somewhere here. Then it means that this guy will make the major contribution to trap-assisted recombination. Also, of course, per single defect center, because it can be high concentration or low concentration. So that's difficult to say in the general, but per single defect center, this will be the most efficient recombination center. However, at the same time, these tail states, they are much shallower. So they are closer located to the bottom of the conduction band and top of the valence band. And their efficiency as recombination states, centers, will be not so high. So it makes sense to introduce some quantitative parameter which will tell us okay, we will divide band gap in 3 regions. And let's say we have EC, EV. Let us assume that we divide this band gap in 3 regions by so-called demarcation energy levels for holes and electrons, EDP, EDN, and in this region, let's say it's region 1, all localized energy levels which are located in region 1 will work as trap centers. Means they will trap charge carriers, they will keep them at this energy level without recombination, and over some time, because of thermal activation, they will just detrap. So we have trapping effect event and then detrapping event. From your point of view, this presence of such energy levels, will they affect concentration of non-equilibrium charge carriers in semiconductor or not?
I think no, but can I proceed with the question?
So you are right, it's not, because if we have shallow energy level within the first region, it will act as efficient trap center, but will not participate efficiently in recombination. So why? Because probability of detrapping, if we have a trapped electron at this energy level, the probability of detrapping the electron will be higher than probability of trapping hole from the valence band, because this energy level is located very far from the valence band. So probability will be higher for detrapping than trapping. So means this this energy level will not have much of contribution towards reduction of charge carriers via trap-assisted recombination. However, there is one parameter which it will definitely have negative impact on. Any ideas which parameter will be reduced?
Electrons in the conduction band, the carrier electrons in the conduction.
Okay, that's good start. So they are mobile. And when they are trapped at this localized energy level, they are not mobile anymore. So they are localized. During all this time, it stays trapped at this energy level. It cannot move anywhere. And that is not good for us, because we always want to take out something from our device and run it in the external electric circuit. There is a parameter which defines how fast electrons can move in external electric field. There is mobility of charge carrier, mu. We will discuss it a bit further, but I'm sure you heard about this parameter, this characteristic previously. So the mobility of charge carriers will be negatively impacted, because part of their life, they have this recombination life, their life is limited. They don't live forever. But part of their life, they, instead of moving and being extracted from the device, they will be trapped and will not participate in charge transport. So now let us consider region 3. We will skip region 2. It will be region 3. So if we look at region 3, and here is some energy level, these energy levels located in region 3, they should be associated with holes traps. Means it can easily trap hole, and the probability of detrapping hole back to the valence band will be higher than probability of trapping electron from the conduction band. So it will be the same story. They will not participate in the reduction of charge carrier concentration, but they will reduce mobility of holes. And that, of course, is not good, but in terms of recombination, it will not be efficient recombination center. Obviously, there is still a possibility that recombination will happen, but this possibility is low. And we need to have really high concentration of these shallow energy levels in order to get some recombination via them. That's why we actually do this integration, in order to take into account all possibilities. But the fact is that efficiency of recombination processes via such traps for electrons and holes will be very low. And of course we have this region number 2, and this region number 2 corresponds for deep energy levels, because they are located somewhere far away from both valence and conduction band, and energy levels located within this region number 2 means deep energy levels. The probability of recombining, so if we have trapped electron, the probability of getting this trapping another hole will be higher than probability of detrapping. Means if electron or hole initially are trapped, the most favorable and most probable process will be not detrapping but recombination. And that means that it will not have a big impact on, noticeable impact on mobilities of charge carriers, because we just don't have any more of these charge carriers. They will vanish, they will recombine. So obviously these energy levels located within the region number 2 will have the most important contribution towards the reduction of charge carrier concentration, means the net recombination, trap-assisted recombination rate. So now what I would like to do, after giving you this qualitative description of demarcation levels, I would like to show how we will determine them quantitatively and consider where exactly they are located within the band gap for given semiconductor. So let me go out from this presentation. Oops. Yes. Okay, so we consider some energy level next to conduction band. So this is EC. Here we will consider some level ET, and trapping rate of electrons on this energy level. Make it a bit thick.
Question. I have a question about, so in case we have a temperature change.
Temperature change.
Like for a room temperature change.
Okay.
You said that the electrons that are trapped in the conduction band, under the conduction band, including the conduction band, are expected to first detrap.
So for each temperature, doesn't matter if you keep temperature constant or you change it, you will eventually get equilibrium condition. So we have some rate of trapping and some rate for detrapping. Under equilibrium condition, both rates should be equal because they kind of compensate each other. So if we increase temperature and detrapping increases, then also trapping should increase. Why? Because if we increase detrapping, we increase number of empty spaces and not occupied energy, localized energy levels. And this concentration of non-occupied localized levels will increase probability of trapping. So we will always go to some balance between trapping and detrapping rates. So let us mark trapping and detrapping rates as T and D. So for trapping rates, we can write that it will be equal to concentration of electrons in the conduction band, like mobile electrons in the conduction band. Then we have their thermal velocity, like speed, cross-section area, sigma n, and actually number of available localized energy levels which are not occupied, means total concentration of these defects minus NT, which is concentration for trapped electrons. So this will give us the number of trap events per unit time per unit volume. So now detrapping. Not good. Detrapping rate. Detrapping rate we actually remember from previous discussions also. We have some coefficient alpha n, which gives the efficiency of detrapping process times concentration of trapped electrons, because the higher number of trapped electrons, the higher probability that some of them will detrap. So we remember that this can be given as V n, thermal speed, sigma n, n1 times nt, because here we need, so this stands for alpha n, and times nt. So as I said, before it reaches some thermal equilibrium, this system, we will get equal T equal to D, means trapping rate will be equal to detrapping rate. So we can actually write that N times Vn times sigma n times Nt minus Nt small should be equal to Vn sigma n N1 times Nt. So now we can cancel out these guys, and we will see that the concentration of let's actually write it here, and we can open this parenthesis, n times Nt minus n times trap charge carrier concentration will be equal to N1 times Nt. So from here we can rearrange and take out from the parenthesis Nt, so it will be N times total concentration of defects equal to N1 plus N times Nt. And from here we can express concentration of charge carriers which will be trapped on this energy level ET in terms of total concentration of electrons in the conduction band, total concentration of defect levels, divided by the sum of N1, which is determined by position of this energy ET, plus again total concentration of charge carriers in the conduction band. So this is the expression for trapped charge carrier concentration. If we assume that we have low level of excitation, then let's say we have EC, bottom of the conduction band, then we have our energy level ET, and here will be EFN. This stands for quasi-Fermi level for electrons. If we don't, like delta N, this excessive concentration is not very high because we have low level of excitation. Quasi-Fermi level for electrons will be below the trap energy level, because the closer EFN will be to EC, to the bottom of the conduction band, the higher concentration of non-equilibrium charge carriers will be. So in that case, we can write that N1 will be much larger than N, because N1 and N, they are functions of position of ET and EFN. If EFN is deeper than ET, there will be exponential function, which is like strong function. And obviously that N1 determined by position of ET will be much larger than N determined by the position of the quasi-Fermi level. So in this case we can take this into account, and the concentration of trapped electrons will be equal to total concentration of defects times concentration of charge carriers in the conduction band divided by N1. So if we have different case when we have a high level of excitation and quasi-Fermi level, so this is EC, this is EFN, and this is ET, is located higher than the trap level, then concentration of charge carriers in the conduction band will be much larger than N1. Then we can neglect with this N1, and we have N in the numerator and denominator. So NT will be actually equal to total concentration of charge of defects in the semiconductor. Means that all defects will be filled with electrons, and they will be occupied with electrons completely, because quasi-Fermi level will be higher than the position of the trap energy level. So now with this we can proceed further and discuss the definition of these demarcation levels, which will give us this option, quantitative possibility to distinguish between traps and recombination centers. So let us go to another slide. So I said that energy level will be considered as a trap if the probability of detrapping will be higher than probability of recombination act. So for instance, for electron will be higher to detrap back to the conduction band than to trap a hole and recombine. So for detrapping, probability of detrapping and demarcation level should be an energy level for which this process have equal probability. So then we can write for trapping that NT concentration of for detrapping concentration of trapped electrons times Vn times sigma n times Nc exponent minus Ec minus Edn divided by Kt. So this guy stands for N1, but we assume here instead of trap energy level this demarcation energy level, for which probability of detrapping and trapping, detrapping of electron and catching hole from the valence band will be the same. So here we put actually probability of this energy level to trap hole from the valence band. So that obviously will be proportional to the total concentration of holes in the valence band, thermal speed of holes, capture cross section of a hole, and number of available electrons on these energy levels in order to recombine. So we need to put here NT. So if this left and right are equal, we have the condition for this demarcation energy level for electrons. From the left side determines us, gives us probability of detrapping electron from this energy level, and the right side gives us probability of recombining act between trapped electron and hole from the valence band. So now we can cancel these guys, assuming that Vn is about equal to Vp. To make it easier, we can also cancel this. We have only Nc times exponent minus Ec minus Edn divided by Kt, and this is equal to P. Oh, I made a mistake. We don't need to get rid of these guys because they are different. So P times, so here will be sigma n, and here P times sigma P. Okay. Now we need to express Nc. What is effective density of states for conduction band? What is definition of this Nc? So we can write that concentration of charge carriers, equilibrium charge carriers in the conduction band is equal to Nc times exponent minus Ec minus Efn divided by Kt. So, sorry, this is not equilibrium charge carrier, this is total charge carrier because we use here Fermi, quasi-Fermi energy level for electrons. So now we can express Nc from this equation. So Nc will be equal to n times exponent. Already no minus, it will be Ec minus Efn divided by Kt. And then we substitute this Nc in our previous equation. So we will get sigma n times exponent Ec minus Efn divided by Kt times exponent minus Ec minus Edn divided by Kt, and that is equal to P times sigma P. So from here we see that Ec will cancel out because we have here minus and here plus, and we can write that it will be sigma n times exponent Edn minus Efn divided by Kt equals to P sigma P. We can rearrange this in order to get what we are interested in is this numerator of the argument of exponent. So we can write that Edn minus Efn is equal to natural logarithm, actually Kt times natural logarithm of the ratio P times sigma P divided by n times sigma n. And it can be also expressed. Finally, we can express for position of demarcation level for electrons, Edn, equal to Efn minus Kt. We just change the ratio, flip it over. It will be n times sigma n divided by P times sigma P. So this is the equation which gives us the position of demarcation energy level for electrons with respect to electron quasi-Fermi level. We discussed previously how we determine position of quasi-Fermi level for electrons, and once we know it, with respect to this quasi-Fermi energy level, for electrons, we can calculate based on the properties of the semiconductor and properties of the defect. We can determine position of demarcation energy level. So this same can be actually written for, so let me write it down here, so we have it on the next slide. So it's EDN equal to EFN minus KT times natural logarithm N sigma N divided by P sigma P. So similar, following the similar derivation, we can write expression for the demarcation energy level for holes. EDP will be equal to EFP minus KT natural logarithm of N times sigma N divided by P sigma P. So now, if we consider N-type semiconductor, let's say we have N-type semiconductor, and this ratio N times sigma N divided by P times sigma P will be larger than unity. Then this natural logarithm will be positive. So actually, if we have a band structure, bottom of the conduction band, top of the valence band, then let me change the color. So here will be quasi-Fermi energy levels for holes and electrons. If this ratio larger than unity, actually our demarcation energy levels for electrons and both for the electrons and holes will be located lower than respective quasi-Fermi energy levels for electrons and holes. So this will be E dN, and here we will have E dP. So now when we determined, so first step we determined position of quasi-Fermi levels for electrons and holes, then with respect to them we determined position of demarcation levels for electrons and holes according to these equations. And now we can actually build this, make this division to regions within the band gap. So this will be first region, this will be second region, and this will be third region. So all energy levels located in first region will be considered as traps for electrons. In the region 3, traps for holes, and in the region 2, these deep energy levels will be considered as efficient recombination centers, and they will determine the net recombination rate via trap-assisted or shock-read hole mechanism. So with this, I would like to finish our discussion. Actually, it's already oh, it is. Oh, we have more time. Okay, yeah, I'm somehow confused with this. I accustomed to our general physics course. Sure. So with this we finish the recombination part. We will come back a little bit to recombination when we have surface effects, because there will be also trap-assisted recombination at the surface. However, we already covered the most essential topics related to recombination: bimolecular, radiative bimolecular, trap-assisted recombination. We are deep energy level. We considered recombination trap-assisted. We are localized tails in disordered semiconductors. How we approach this issue, and also we considered how we quantitatively distinguish between traps, localized energy levels, and efficient recombination centers. So with this, we make a transition to charge transport. So obviously, it's not about only generation and recombination. We need in semiconductor devices to take charges out from the semiconductor devices, and that means we need to have to deal with transport of these charges within the semiconductor. So first of all, we will consider motion of free charge carriers in external electric field. So imagine we have some semiconductor, we have, for instance, electrons in the conduction band. They are mobile because energy levels within the conduction band are delocalized, and we create some internal electric field, let's say E, with magnitude E. So then so-called drift speed of charge carrier will be determined as follows. We have elementary charge of our charge carrier, in this case electron. Then we multiply it by electric field, so it will be electric force exerted on this charge carrier, divided by effective mass of electron, which will be different from mass in free space because of periodic potential of the crystalline lattice, and times some average time this charge carrier can move upon the influence of electric force without interaction with the crystalline lattice. So means that during this time it actually can accelerate, because this term stands for acceleration. It's force divided by mass. So it stands for acceleration according first law of Newton and of motion, and then we get some Vd velocity, like drift velocity, if we consider it's in vector form, which its direction will coincide with the direction of internal electric field in the semiconductor. So it is possible to express this in a bit different form. It can be also written as mu n times electric field vector. And mu n is that important parameter, which is mobility of charge carriers. In this particular case, mobility of electrons. It is, by definition, is drift velocity which charge carrier gains in the unit electric field. So when magnitude of electric field is 1 volt per meter, then the velocity of drift velocity will be equal to mobility of charge carriers. And the units for mobility are centimeter square divided by volt times second. So if we have electrons as mobile charge carriers which can contribute to electric current, so the current density J, amperes per square centimeter or per meter, which is carried out by electrons, will be equal to charge of electron, their concentration times drift speed. And in terms of mobility, we can express it as mobility times electric field is drift speed. So it will be Q times N times mu N times electric field magnitude. So similar we can write for holes, because we have two types of charge carriers. We have electrons in the conduction band and holes in the valence band. So here will be J times P, Jp equals to charge of hole times concentration of holes times V dP. And that will be equal to Q times P times mu P times E. So we have mobility for electrons and for holes. Why they are different? Because effective mass of electrons is not usually equal to effective mass of holes. So mobilities are also different. Now the total current in the drift, so-called drift current in the semiconductor will be the sum of hole and electron component. If we want to determine, for instance, specific conductivity, like sigma of this semiconductor, this will be according to the Ohm's law in differential form, J divided by electric field magnitude, and that will be equal to the also to two contributions originated from electrons and holes. So n times mu n plus q times p times mu p. So this stands for drift contribution, and it happens obviously only when we have some electric field. However, there is another contribution to charge transport, and that contribution is diffusion. So diffusion happens when we have some gradient of concentration. If we at some point of semiconductor have excessive concentration of electrons or holes, we will observe some gradient of concentration, and this gradient of concentration will drive charge transport via diffusion mechanism. So from your point of view, what could be the reason for such non-equal distribution of charge carriers in semiconductor? So how can we create this condition?
Make a diet. Make a diet.
Sure, make a diet, but let's so far stay in the material, like pure, pristine material. We don't have so far.
Heat up one side, but cool down.
That's one option. Another option, we can shine light from one side and we absorb and photogenerate. Or if we have some electrodes to a piece of semiconductor, we can inject charge carriers with one electrode, extract charge carriers with another. Obviously, there will be also some gradient of charge carrier concentration. So, in case of diffusion current Jn carried by electrons can be expressed as charge of this electron times so-called diffusion coefficient, which describes how some kinetic features of charge carriers in the material, how easily they can actually move there, and times first derivative of charge carrier concentration along the direction which we consider for studying charge transport. Since we deal with most cases, we have planar devices, and we deal with single dimension case, we, instead of writing gradient of charge carrier concentration, which implies considering it in three-dimensional space, we can just operate with the first derivative over our position along one axis, which is axis x, for instance. So, and that is valid for really great range of semiconductor devices, because most of them have planar device architecture. So we really take care how charge transport happens in a single dimension. If devices are of some extraordinary device architecture, then of course this three-dimensional case should be considered, but that makes life much more difficult. So electric current carried by holes because of diffusion will be given as minus times q. So minus because of the charge, so it's opposite charge to electron is positive, and the direction of current is actually opposite to the direction of the gradient of charge carrier concentration. So that's why for electrons we don't have minus, for holes we have minus q times dp times first, this is diffusion coefficient for holes, and times first derivative of holes concentration over this position along axis x. So now we have second contribution. There are actually two contributions. When we deal with charge transport of charge carriers in semiconductors, there are two contributions. Drift, when we have electric field, and diffusion. So obviously the total current under any conditions for semiconductor device or semiconductor sample should be as follows. We have some, I can write it in a vector form also, total electron current in semiconductor material, which is equal to drift current carried by electrons plus, so it's also electrons, diffusion current, and that will be equal to q times n times mu n times electric field vector plus q times dn times dn over dx. Then for hole current we can write also two contributions, P drift plus J P diffusion, and that is equal to Q P times mu P electric field vector plus, sorry, not plus, but minus Q dP times dP over dx. So now we have these two equations which actually describe charge transport in semiconductor samples and devices. Here we have two parameters, like in each of these equations, we have two parameters which are features of charge transport in semiconductor, mobility and diffusion. So what is important to underline here, that drift and diffusion as charge transport, they are not completely independent processes. Obviously, mu n and d n should be somehow dependent on each other, because they are, like, both of these parameters describe how easily these charge carriers can move in semiconductor material. That's why it is actually there is some named Einstein relationship between mobility and diffusion coefficient, and we will try to show it actually now. So how much time do we still have? 0. 0. Okay, then we will show it at the beginning of next lecture, and we will show that indeed there is a simple and quite straightforward relationship between mobility and diffusion coefficient for holes and electrons, assuming that we have so-called not degenerated semiconductor. So means when it's not extremely heavily doped, and Fermi, quasi-Fermi, like Fermi energy level for equilibrium condition is not located too close to bottom of the valence band or the top of the bottom of the conduction band and top of the valence band. So today we finished our discussion of trap-assisted recombination and started charge transport in semiconductors. So thank you very much for attention. If you have any questions, you're welcome. Hope to see you next time. It will be on Tuesday. So we have this spring break. Okay, then we will see you already after spring break. Good, then have a good day and take care. Bye.